Hello, everyone. Thanks for joining us today. Today we have Jeongyeol giving a talk. Jeongyeol is a postdoctoral researcher at the Wisconsin Institute for Discovery at the University of Madison, Wisconsin. The research interest is in reinforcement learning, optimization, and application to adaptive decision-making systems. Before that, he obtained his PhD at University of Texas, Austin, and is supported by the graduate continuing fellowship and the Kanjong Foundation Scholarship for Graduate Studies. Today is talking about RL in Latent MDPs, is Tractable, online guarantees via of policy evaluation. Thanks a lot for accepting our invitation, and the stage is yours. Thanks again.
Yeah, thank you. Hi everyone, and thank you for joining the talk. I'm Jeongyeol. So today I'll talk about my research, which has been basically about optimal adaptation to hidden contexts with reinforcement learning. And this is a long time joint work with Konstantin, Shai, and Jonathan. Before starting, I wanted to take a moment to thank to the organizers. So it's really great to see that the seminar series is kept running since last time I gave a talk, which was 4 years ago. So I'm really happy to come back here and present more findings after I've done my homework. So thank you for inviting me again. And I'm going to share what I've learned the past few years about latent MDPs, and hopefully we can think about what will be the next. So in the last decade, we have seen many successes of AI, starting from AlphaGo. It surpassed the human intelligence in many difficult tasks like robot arms, StarCraft, ping pong, natural language processing, and math competition, and whatever, so on. And behind all these successes, the reinforcement learning researchers know that there was always reinforcement learning behind that created those wow moments. And so today, many people, even outside of our community, challenge us whether reinforcement learning can really solve the real problems, which is the ultimate goal of our community. And so at the technical level, I think this means we need to handle the question, can reinforcement learning algorithms handle noisy observations and uncertainties in real-world tasks? So most reinforcement learning theories are well supported under the Markovian assumption, but many real-world problems does not have that nice property. And so out of this broad question, my research has been focused on how we can adapt to hidden contexts sample efficiently. And so that was the main theme of my research. So here's where my problem comes from. Imagine we want to solve a medical decision-making problem. I have a hospital. So a patient visits my hospital, and she showed me some symptoms of cold. I assume that it must be just a cold, so you'll be recovered in a few days. So I just gave him a light prescription and sent him back home. A week later, he came again, saying that I'm still sick, and actually it got worse. So then I got a deeper examination, and then found out that, oh, I'm sorry, you got COVID. So I got him hospitalized. So we are all humans. This kind of thing can happen in our life, but it's not a good decision-making process because it's dangerous to assume something that you are not 100% sure that you are not observing, especially in situations where stakes are high, like in healthcare. And besides things like virus, there are other subtle human factors, such as the patient's personality, whether he will follow my guidance properly, or there could be some private factors that the patient doesn't want to tell, or genetic factors that can only be built through expensive medical tests. So there are many hidden contexts in real-world problems. And if you look around, it's not just the story of healthcare. For example, in recommendation systems, some users don't want to share their private or transient user information, but still they want to get to the item that they want as fast as possible. Also in robotics, real experiments are expensive, so many training happens in simulators. But once it's deployed, it has to adapt to the real world quickly. So in that case, the hidden context could be the unknown physics parameters, like frictions or object weights at the test time. Even in financial markets, if I do day trading, I sometimes wonder if there is anything I'm missing in today's market. So there are lots of partially observed systems that can be also viewed through the lens of hidden contexts. So my research has concerned, can we learn decision-making systems sample efficiently? And I'll define what sample efficient I mean in this talk precisely later, so that we can optimally adapt to such hidden contexts. And so I'm going to share what I've learned in the past few years about this question. So this talk will flow in the following steps. First, is the problem learnable? Meaning that, is there a sample efficient exploration strategy to find the optimal policy? And answering this question took us beyond the Markovian world, and we need some new theoretical tools to answer this question. So I'll also go over the algorithmic insights, and then get into our some of technical concepts and ideas we developed for our proofs. Okay, so the problem setup. The framework consists of state space, action space, and real-world space. Here we'll focus on tabular settings. I'll sometimes use the notation X to denote a pair of state and action. And we're going to assume that reals are bounded here. And if the symbols have subscript t, that's a realized random variable at time step t. And we are in the episodic setting. So far, it's a typical MDP. Then we have a hidden context. So I'll assume this hidden context is also a discrete random variable, like a gender in an anonymous system. And it's randomly decided at the beginning of each episode. And then the environment is going to be a set of interaction dynamics. So the interaction dynamics can be different across contexts. Here, I'll use the notation P of M, given the next of probability of the next state and rerolled, given the current state and action. But implicitly, they're also conditioned on the hidden context of the system. And of course, these probability distributions are not known, which is typical in the learning setting. So overall, the process would look like this. So the interaction with each patient follows a MDP, but the MDPs across patients can be different depending on their contexts. So think of their context as some kind of like genetic vectors that you cannot observe directly. And we want to avoid an expensive medical test from the start. The goal is to maximize the expected cumulative rerolls over all populations. So this objective is also averaged over the entire population. So you can also think of it as the Bayesian rerolls. And the policy that we want to optimize is history dependent, because it has to see all the interaction histories within each episode. And the notion of optimality here is actually the Bayesian optimality, meaning that our competitor is the Bayesian optimal plan who can play the best if all the environments are known in advance. And we are not going to worry about computational constraints in this talk. We'll just focus on the sample efficiency. So if we knew the prior distributions exactly, then we assume that we'll immediately get the optimal adaptive plan can be computed. So I'd like to start with a small example to see what's a big deal here. So imagine we want to understand how effective a new drug is as a part of the personalized treatment plan. So we have two hypotheses. Let's say in one hypothesis, there are two groups. One group is less likely to respond to the drug, let's say with probability 1/4. The other group is probability 3/4. And if this is the case, we want to find some better personalized plan depending on their context. In the other hypothesis, let's say there is no such group distinction, and all patients will just respond to the new drug with probability 1/2. But it's a new one. It's a new drug, so we want to be careful. So there are restrictions on how many times we can prescribe it to per patient. And so let's say if we are only allowed to try the treatment once per patient, can you figure out which hypothesis is right? And then would the story be different if we can test the same intervention twice per patient? So I return to the answer to these questions, but you might already have a sense of where this is going. And the real challenge is, can you say something more general when there are arbitrary number of groups, constraints on the allowed actions or the interaction dynamics? Because they can be all unknown, latent, and also possibly limited by we are allowed to do in the real world. So understanding the key challenges in this example was what I was dealing with in my research, and I'm happy to share the foundations that I found through this kind of studying this problem. So the main contribution of my research has been to provide the provable guarantee with an exploration algorithm for a general tabular setting with any number of groups or contexts, and with any constraints on the action choices or the interaction dynamics. And I'll prove that this can be done sample efficiently, which I'll clarify what it means in the next slide. The aim of this talk is going to develop a sample efficient exploration strategy for latent MDPs. So are there any questions so far about the setting?
I think I'm really good. So on the previous slide, you were talking about these two cases. So just to clarify here, even if I know in which hypothesis I'm in, if I can only use the drug once, it seems that, well, I can't really do much. My observations are probably not going to give me any information about which group we are talking about, whereas if I can use the drug twice, then the observations might be revealing something. Exactly. And then the second time you're using the drug, you can be clever about what you're doing. So it should be all about even a baseline, right? Like in a way, the first problem is kind of easy because everything is equally bad. Mm-hmm. Like you cannot really specialize. You might think that it's hard, but it's actually easy from the perspective of like, you don't really need the latent information to act well. In the other case, you actually need the latent information, and knowing the latent information makes the difference. Is that, yeah?
Exactly.
Describes
exactly.
what's going on?
Yeah.
Okay, good. Sounds good.
All right.
Yeah.
Okay, so so let me go briefly over how this work is going to be positioned in the literature. So this is the partially observed system, but there's a reason that we don't just want to consider a problem as a general POMDP problem, because it is sort of well known that the general POMDP is hard. The main issue is that there is no better way other than considering the entire history as a separate state. So the effective size of the state space blows up as the interaction horizon grows, which is known as the cursor horizon. So reinforcement learning theory has been 99% of about how to break this cursor horizon with some clever exploration strategies whenever there are problem structures that we can leverage. So MDP is one such representative case. So in this talk, by sample efficient reinforcement learning, I mean we are interested in whether there exists a non-trivial exploration algorithm whose sample complexity does not blow up with the growing interaction horizons. And there has been quite a progress recently in identifying some bigger class of tractable POMDPs. For example, Liu et al. Characterized a large class of POMDPs that finds a nice middle ground between MDPs and POMDPs. So many of settings like block MDP or weakly revealing POMDPs, I think they are fall into this category where the settings are mostly motivated by scenarios where observations are rich. So there is always a decodable function from the observation to hidden states. So the game is more about how we're going to efficiently filter out the unnecessary or irrelevant information when such decodable function, when such decode function is not known in advance. My latent MDP work aimed to complement the literature in a sense that the game is more about how to collect the information about the hidden states. And once we collect the information about the hidden states, we're going to leverage it for adaptive decisions in later part of the episodes. So this is a quick summary table of the MDP literature that I found so far. By no means, this is a complete list of the literature. I just listed some relevant modeling frameworks that have been studied recently. So each framework has their own assumptions or structures for sample efficient learning. For example, for tabular and linear MDPs, it is more or less, I would say, it's solved. And so a larger portion of work now is devoted to solving block MDPs or low rank MDPs inspired by like high resolution observations like images. Then there is a exogenous block MDP formulation, which also considers some temporal correlations in the irrelevant features. And then there are also M-step decodable MDPs, which is kind of like mth order block MDPs. And then there is a weakly revealing MDP. So this work. That weakly revealing MDP has been really the breakthrough. I think it was really a nice work, giving us lots of insights. But there are some technical things that we need to resolve if we want to also solve latent MDPs. So in their technical assumptions, they require a certain degeneracy assumptions about the emission dynamics, meaning that a certain mapping from the latent state to observation has to be in a full rank. And also they have to know the set of policies called the core tests in advance. So the tractable MDPs there is defined over the classes where this set of known policies works as a core test. So technically speaking, the biggest difference from that weakly revealing MDPs and our work is, first, we do not assume that the number of contexts are fully specified. So there could be at most 3 groups, but there also could be 2 groups and so on. So this full rankness assumption will not hold. And second, there is no a priori known core test, which was the key mechanism used in their exploration process to decode the belief state. So, and without the support from these 2 assumptions, we need to develop some new angle for sample efficient exploration. Yes, Chaba?
Yeah, this core test assumption, I don't know which paper you're talking about.
So there are some extensions about the predictive state representation.
Yeah, so are you talking about the optimistic MLE paper?
Yes.
With Xinhua?
Yeah.
I don't really recall this. Maybe I'm wrong, but yeah.
So they used a short sequence of random exploration when they explore. That's sort of like the core test is assumed to be.
But no, it's not. Yeah, like it was a key of that paper that these things do not need to be known. They're going to be discovered by being optimistic. It was actually pretty important in that paper and the previous paper as well. But like, okay, maybe you can take it offline, but that's how I remember it. Yeah. So then there would be the question of like, is your setting a subcase of this or not? If this core tests do not need to be known, do you know the answer to that?
So from my understanding, for all MDP works that has been known to be tractable so far needs this core tests so that after running a policy certain times, you want to know what's the belief state of that history, but because you cannot observe the belief state of the history, instead you are mapping it to a certain prediction over your futures. And for revealing that prediction of your futures, it has to be some tests that is meaningfully differentiating the future observation probabilities
Right.
when the frequency is different.
Yeah, so it's about the differentiation, but it's not about knowing how to do that. Like you don't need to know, but it has to exist.
It has
right?
to exist.
But
And
I think that it's like if that doesn't like, is that true that in your assumption these core tests would not even exist?
that's
So
true.
there is no way of designing some action sequence that let's say is that makes the information about the state distribution kind of known. Is it true?
So
that condition will not be met. So that's what I would call the geometric condition that
exactly.
like that some revealing info, like there must exist some ways of decoding, but from observation sequences it's not from rich enough observations or anything like that. That's not needed. If your sequence is long enough, then maybe that long enough sequence kind of reveals the information about what was the state so many time steps before.
Right.
So then the question is whether in the latent MDP setting that you can have positive results for, is this assumption not met?
So the most trivial case would be if there was just one group, and then I'll assume two groups, then the degeneracy will happen. Like if you assume 5 groups, but there are only 3 groups, that's also the case. And also, so if most of the actions, all of the groups respond the same, but there are only a few actions that they become to distinguish, then unless you know which actions making a difference, you have to find a way to explore what are those actions that are revealing about the context.
I mean, in this revealing MDP work, the complexity is going to depend on the length of the action sequence that reveals the information, and it's exponentially, the complexity is going to be exponential in this length, exactly because the algorithm effectively searches through all of these action sequences. So that's how you kind of avoid the need to know these things. So maybe this is what you need, and you are able to avoid this, I assume.
Right. Yeah. That's the whole point of trying to avoid that kind of issue was
right. Yeah. And the price is that the number of contacts is going to appear in the exponent, though.
Exactly.
Yeah, it's kind of like a different complexity measure.
Yeah.
Okay. Cool. Yeah. Thank you.
And just one thing, the fact that so the meaning that I said core tests need to be known. So it's actually for the exploration you need to run some sequence of random actions. And so in my interpretation, in that case, the core test is the all possible sequences of the short lengths.
Okay. So because the algorithm essentially uses randomization to exhaustively search in that space, you might as well assume that they are known because there is no magic there. I see. Yeah, that's true. That's totally true. Okay.
So I also mentioned that this formulation probably for practitioners might be also familiar. It's the same formulation to base adaptive reinforcement learning or meta reinforcement learning in more applied settings. But basically, my understanding on this literature is, and I could be wrong, so please correct me. Most of the Bayesian RL settings, I think they assume either the population distribution or the prior is known, or they can pre-process with some lifelong clustering. And often the goal is also different, like they are measuring different regret measures or more focusing on the empirical results.
Sure.
So I'll not go I'll not go deeper into the literature review here. But yeah, please let me know if there is any other clarifying questions.
Sounds good.
Yeah. Thank you, Chaba.
Yeah.
So let's get into the high-level algorithm and guarantees. So the first to think about is how we should tackle this, even the simple case of two hypothesis testing problem. So the idea starts from here. We wanted to know whether there are separate groups that respond to the drug differently, or whether there are no such group separation. But if we can only try one test per patient, the situation is tricky because when our observation, the probability of success is going to be 1/2, but we don't know whether it is coming from the randomness of the process itself or the randomness of the population. So in this case, they both seem identical. But if we can try twice per patient, then we can measure the successive, measure the probability of both test successes. And of course, the course assumption here is the test from each individual will be independent. But that's from a mathematical standpoint, it's worth considering because it can be generalized to other cases. So we're going to see the different probability of success of both tests being successed if we collected the correlation data over all populations. So basically the mechanism is, okay, out of H interactions, we're going to apply this drug twice at some point, and then we're going to estimate the correlations up to certain accuracy, and then we're going to find the hypothesis that match. So that's what we can do when we can try the same drug twice per patient. So now coming back to the original setting, what if we can only still try once per patient? So this is like the policy. This is like the patient will never be given be in the same state again, or there will be no same as will be shown to the same user in the same session. And so in this case, we have to read something from the results of different items at different stages. So here we do not know how correlated the two different items are, but still we can measure something about the responses to these two different items. For example, if I found a patient is allergic to a stronger pain reliever, then later stage I can infer that the same line of medicines will be problematic. So I can decide which medicines I'm going to use in the later stage, even if it's not the same action. And so this is the correlation that I can measure even between different actions. And this is learnable because we can observe the responses to these actions jointly, and we can collect that observations over many populations. So correlation is an observable measure, and that's going to be how we can sidestep the issue of we are not directly observing their contexts. So we can abstract the idea. So when we can say there are cases when we can say there are two distinct groups, and there are cases when we don't much care about such hidden structure. And so the answer is quite simple. If we can find any pairs of actions whose responses to those actions shows a strong correlation, then we can say that there are already two underlying groups in the population. And if we cannot find any pair that shows such strong correlation, then it means we don't have to worry about the hidden context because they will not make any differences in our decision-making process. So we can write it down, this intuition, as a brute force search algorithm. Basically, we can first try all allowed pairs of actions per patient or users as much as possible, and then see if we can find any strong correlation patterns we can find. Then after that, we can identify the correlation matching hypothesis. And then with the matching hypothesis, we can plan the base optimal policy. And the search targets were the pair of actions, or more generally state actions. So the search space is going to be limited to S square, A square. So this was the initial result when there are only, we assume there are at most 2 contexts, and how can we find an optimal additive policy in this case? So can you say something more general? And the extension to general number of contexts can be extended using this correlation matching principle. This correlation matching or moment matching is a very classic, but still a powerful tool to handle latent variable models. And so most of my effort has been putting using this principle into decision-making settings. So basically, the intermediate result that we have shown for general number of contexts was this performance difference lemma for latent MDPs. That is essentially a policy evaluation guarantee. So let me explain a few notations here. So V hat is the evaluated value of a target policy, and V is the true value of the target policy. And that P of pi inside the arrows there, that's the probability of observing that set of treatments as a subsequence that I've observed in an episode. And then the delta there is the estimation error about the correlation between these set of treatments. Yeah, so later I'll get a clarifying question. So here, the bottom line here is D is the intrinsic degree of correlations that we have to match. And that's the system property, and it does not grow with the interaction horizon. Like D equals 2 when M equals 2. In the MDP case, M equals 1, so D equals 1. And if you set D equals 1, what you get is the usual performance difference lemma for MDPs. So you can also think of it as the generalization of the first order performance difference lemma to higher order performance difference lemmas with hidden contexts. So to summarize, the idea is to explore and match only the reachable correlations, and that's enough. And the specific configuration of the degree depends on the additional structures we can leverage. So if we don't assume anything more, then D is going to be as large as the number of contexts. So mostly useful only for a small number of groups. If we assume more structures, and I believe there will be more interesting structures to recover, but one interesting example was if the responses to those actions were deterministic given the context, then the required matching degree drops to logarithmic. Anyway, it says that the sample complexity depends on this intrinsic degree and not growing with the interaction horizons. And that was the key to obtain a sample efficiency result. So yeah, at this point, please let me know if you have any clarifying questions here. Yeah, Chaba.
Yeah. There is a condition that says expiration is easy. What's the meaning of that?
I'm gonna go over it right next.
Oh, okay. Yeah. Postpone it. Yeah. Okay. Oli is asking, does the algorithm need to know D?
So we only need to know the upper bound about D, but then the exponent will also depend on that upper bound. So
don't you do some doubling? You don't know D, and then you just try, and then you get bigger and bigger and bigger, and then eventually figures it out.
I think that would be also possible. So actually that I discussed with Uni for some time when we don't know the exact number of contexts. Yeah, I think that's a possibility. I didn't specifically dig into that setting yet.
Okay. All right. Sounds good.
Okay, so now let me come back to the theorem statement. So there was one sneaky assumption that I'm now going to talk about. So for this lemma to hold, in our intermediate result, we required that the state transition is not affected by the hidden context. So what this means is that basically the exploration is the context is just a matter of preference. It's just affect the reward distributions like the patient satisfactions, but they do not matter for the overall success of the treatments or new state exploration. And so, but this was quite restrictive from both theoretical and practical perspectives. And we've been struggling for a while to get rid of this assumption. So let me explain it a little bit more in detail. So when we say exploration, we want to know a certain policy that gets us to a certain state. And we don't know how to get there initially. So we have to try a bunch of things to figure out how to get there, what's the right policy to get there. And reinforcement exploration is mostly about how we're going to do this exploration efficiently. But now if we have a hidden context, so if the right policies can be different across all contexts, it gets tricky here. For example, we want to improve the patient's states by applying a proper treatment plan. Let's say we found one plan for some patients. So after they got better, we want to move on to a lighter treatment, like plan B or C. But then from then, we found that C never worked out there. So we removed C from our consideration. Now, what could go wrong here is, so the plan A only worked for the first type 1 patients, but the type 2 patients needs plan D, let's say. And then they need plan C afterwards. So in short, the exploration gets harder because we cannot observe which sequence of experiments have succeeded to reach there under which context. And this ambiguity accumulates as the interaction horizon gets longer to get from one starting state to another state. And the rate of this ambiguity getting accumulated has been exponential if we are not careful. So for a while, we couldn't show that how the efficient exploration happens without compounding that ambiguity exponentially over the interaction horizons. So that's why our initial results we could only give it for when this exploration was easy. So the road for exploration has been blocked. We decided to take a detour, and that was actually looking at the offline setting. So the goal here is to evaluate a bunch of new candidate policies given the data collected with the different policy, and what we call a behavioral policy. So the mission here is to evaluate a new policy given the data set. Of course, we cannot always evaluate a new policy if the coverage is bad. That's why we studied the notion of coverage in the offline setting. And the question here is, if there is hidden context involved, how we're going to define that coverage concept. So again here, the hint was in correlations. So the coverage in latent MDP is defined by how often you are likely to observe a certain set of treatments under every context. So what we want is a comparison measure between how often the two different policies will observe or reach the different set of treatments to observe correlations from the same group of patients. I'll revisit the precise definition later. And here I'll just focus on the high-level sense. So with this notion, we could give a off-policy evaluation lemma. Basically, written as it is seems standard, but the point is here, the policy evaluation error is going to be proportional to the correlation coverage coefficient. So, so this was the main puzzle piece for online exploration, which I'll explain in the next slide. By the way, I'll just briefly mention that for this offline evaluation lemma to hold, there is a caveat. For now, for technical issues, I can only show this for more or less memoryless policies. And it's a policy evaluation problem for general policies still remains as an open problem. And memoryless, I mean the behavioral policy has to be memoryless. Although the evaluation policies can be arbitrary, history-dependent policy.
Right. Otherwise, we would be in trouble with what's coming next. Okay, good.
So with this off-policy evaluation result, the trick is simple. Actually, if you are familiar with the coverability argument, this might come naturally. So we're not going to estimate the correlation coverage coefficient exactly explicitly, but we can say something the other way around. So the algorithm will interleave over online exploration phase and off-policy evaluation phase. In the first phase, we're going to search over the policy whose evaluation is likely to fail, because then it is an evidence that the policy can explore new correlations under some new context that has not been visited in previous rounds. So now we're going to generate new trajectories with the exploration policy generated by our algorithm. And then in the offline phase, we're going to update our model parameters to match the newly found correlations. But basically, this is about this part is just the activity distance learning or maximum likelihood learning. So that part is more or less using a standard maximum likelihood estimation tools, how we're going to get the correlation matching hypothesis. And we're going to interleave this process until we can evaluate all policies. And that's how we got our May theorem. So the statement is just saying that the optimal policy we can learn the optimal policy without suffering the curse of horizon. And with the fact that the degree of correlations that we want to explore does not grow with the interaction horizon, this became the first theoretical result to break the curse of horizon for latent MDPs. And this result has been developed through multiple publications. So in our earlier result, we only had the matching lower bound, which I presented in 4 years ago. And then we got some intermediate specialized results for context-free transitions. But then today, I'm sharing the upper bound, how we got the upper bound results. So any questions so far?
I'm good.
So for the remaining time, I'll just go a little bit deeper into actual algorithms and proofs. And before getting in, I'll say that the current proofs and definitions are by no means optimized. So, and this is a unique style of argument. So I was barely able to formalize the intuition. And some of the steps might feel hand-wavy or brute force, but I think there are lots of future opportunities to tighten those results. So my approach begins with the proposed concept of policy segmentation. Here, the circle subscript means we run a certain policy, and then at this, when we reach this time step, we're going to switch to next policy with the memory reset, meaning that we're going to empty out our history buffer and then start start running the next policy as if we are starting from scratch. So what this is all about? So imagine we want to estimate a correlation. Then what we have to do is we want to explore a different set of states and actions. That's like a set of treatments applied to at proper states. So we want to visit these state and actions sequentially. And this what construction aims to do is running pi 0 until we get the first target, and then run pi 1 until we get the next target, and so on. So ideally, in this segment construction, for each segment, we'll aim to execute pi I that maximizes the chance of reaching from x1 to xi plus 1, xi plus xi plus 1 under some context. And then now I can precisely define the correlation coverage coefficient that we used in our proof. So in this coverage definition, it abstracts the concepts like the first two mixed part is about joint treatments at right timings, and then the joint outcomes of these treatments under every context. And it is run by the behavior. It is defined by the possible ways of constructing the behavioral policy with the segmentation trick. And then we're going to compare the ratio between how often those target states have been reached under each context using the segmented behavior policy and the new policy. Yeah, we have one thing I want to mention here is we have a joint outcomes appearing on the probability as well. This is basically because you can cancel out the reward part here, but we cannot cancel out the next state part because the probability of whether you can reach the next target state and action also depends on where you start. But basically, more or less, this is measuring the probability of whether you can visit those target treatments in this sequential order under every context.
But quick question. So there is state S and X is like action treatment. What is X like?
Oh yeah,
the
X is the notation for a pair of state and action.
I see. Okay. Good.
Yeah. So the off-policy evaluation guarantee for latent MDP, this is stated in its full formality here. There are some minor details I didn't put here, but I think they are more or less the artifact of analysis. So this might look like a standard off-policy evaluation stated in terms of like coverage coefficient. One thing that I want to mention here is you need to execute those behavioral policies that is specifically constructed from that segmentation operation. For example, there are 8 combination D possible time steps when we can switch the policy. I think a more natural switching scheme could have been event-driven. If the math worked out nicely, I think that would also be possible, but the current proof of this lemma is purely algebraic. So there is not much I can say about proof right now. But instead, I'll focus on the implications that this lemma can give, so that how we can design the exploration process overall. So when designing the exploration process, we can control, let's say we can control the right-hand side. The dividends is just on the right-hand side. We can always generate more data. And then the dividends guarantees will be guaranteed by like distributional learning or maximum likelihood estimation. We cannot control this correlation coefficient. We cannot even estimate them. But what we can instead infer is if there is any large gap in evaluation error, if you find any policy that has a large gap in evaluation, then it means this policy, with respect to this policy, our previous behavioral policies have the poor coverage. So if we run this new policy, then we're gonna discover some new correlations. And how we're gonna check if there exists such a policy that incurs a large evaluation error, and that's basically what optimistic M research is going to give us. So just to illustrate how it works in the MDP case, MDP is a special case of latent MDPs. So this is just for like the illustration how it works, but it's actually once you get it, it's kind of natural extension to latent MDPs. So here, if we focus on MDPs, this might be familiar. This coverage notion might be familiar with everyone. And of policy evaluation lemma, in terms of this coverage
question.
Yes.
Q is occupancy?
Yes, Q is occupancy.
Okay, good. It's not Q value.
Yeah,
okay. Yeah. Makes sense.
Yeah. So the typical of policy evaluation guarantee is given in this form. So if you have a target policy, your distribution estimation about this target policy is bounded by how accurate you are on the behavioral policy times your coverage coefficient. Now, on this part, you can generate as much as you want with your behavioral policy. So that part, you can make it nearly zero. And if you still say there is a new policy, some policy that you cannot evaluate well, that means this coverage coefficient has been large, which in turn means there exists some state actions where the occupancy measure with respect to the behavioral policy was nearly zero, but with this new policy, it will be non-zero. So then we're going to run this new policy to cover that new state. And then we can iterate this process until we can no longer find any policy that we cannot evaluate. And there are, in most SA state actions, maybe you can say more if you assume some structures in functional approximation setting. But more or less, this whole process will terminate once all the dimensions are covered, and will terminate. And you're going to get a not only the policy evaluation guarantees for all policies, but also guarantees for the optimal policy. So just how it is implemented in algorithm, find pi-k with large evaluation error. That's what the optimistic MLE construction is going to help you. Basically, any models in the current confidence set is guaranteed to have total variation distance small with respect to the policies that have been run in all previous policies. And then you're going to search over the confidence set, finding over any pairs of models, and search over the policy spaces where this TV distance gets large. And then that means the coverage over some new state with this new policy will be greater than at least twice times any coverage has been made by previous policies. So then we're going to generate this pi-k for some number of samples and to ensure that the next iteration the same logic holds. Now, this can be extended to latent MDPs. So what we're going to start with is the collection of past policies that we have gathered in previous rounds. And then we're going to find a new policy with large evaluation error. And we're going to search for this policy over the memoryless policy space and the optimistic maximum likelihood set. So the nice thing about the optimistic MLE is that this construction of confidence set is very general. It's a distributional learning guarantee, so it holds for any kind of like realizable model hypothesis. And so it also works for latent MDP model hypothesis as well in terms of like distribution learning. And then we can still search over all model candidates and the policy candidates over the memoryless space. Once we found a new policy that has a large evaluation error, this policy will have the coverage at least twice over some segments that we have covered with previous policies that we have found. So we're just going to run this new policy, but in a little bit more structured way to leverage our policy evaluation lemma. So with this newly found policy, we're going to construct the set of behavioral policies that's basically a possible combinations of length D segmentation, with one segment being run by pi-k. And then also we're going to choose the timing when we're going to change. Once we generate trajectories with the possible combinations of the segmentation, then we're going to update our confidence set and we go back to the original, we go back to the next loop and so on. So this process, we're going to end once all segments is going to be covered. So the final complexity guarantee is that at most k outer iterations, this algorithm will find the optimal policy. And the total number of episodes being generated by the algorithm is going to have this complexity result. And then one final mention is basically the outer loop, the iteration number is upper bounded by how many policy segment, how many segments that you have to cover. Like you have to reach from one state to other state under every context. So that's how I got ms squared there, and yeah. So let me wrap up here. So we studied sample efficient exploration strategy in latent MDPs. It's a tractable framework in the sense that there is a non-trivial strategy to break the cursor horizon. And the core principle was the correlation matching or moment matching. And the algorithmic idea we developed is the integration of moment matching into off-policy evaluation. And we used the segmentation ideas for moment exploration. So there are major open questions regarding how to scale up the complexity result. For example, okay, if the sample complexity is dominated by the degree of moments or correlations that we want to match and explore, then even if the worst case degree is always as large as the number of contexts we consider, what if some average models allow us much smaller degree of correlation matching? And that question is two-layered. So one, which models allow smaller degree exploration? And two, given the degree bound, can the similar logic work? And I think the first part is more about understanding the geometric, the mathematical structures in dynamical systems, which might be in a broader scope. But I think from a reinforcement learning specific perspective, the second part could be something that we're thinking about. It could be some other major concepts. And there are also other homework questions like, can you also have hidden contexts with functional approximation or block MDPs? And another question that I think practically interesting would be how we're going to deal with context changes during the episode. So these are, I think, all reasonably interesting open questions. And finally, I'd like to share one speculation that I have in bigger landscapes. So in the past few years, we have discovered many interesting classes of partially observed systems that turn out to be tractable. In tractable MDPs like weakly revealing or weakly observable ones, the key mechanism was to represent the belief state through near future predictions. In latent MDPs, correlation matching is also some kind of like conditional predictions. It's just like, instead of like temporal correlation, it's more like a spatial correlations. So to me, it sounds like there is something about the representation learning paradigm that has been studied in learning for a while. So I think the effort to bridge theory and practice gap could be something that focusing on representation learning. That's my opinion, and I'll also be happy to listen to your opinions as well. And that was it. Thank you very much for listening.
Thank you. Thank you so much.
All right, so the floor is open to questions.
Yes.
Yeah, very nice talk. Maybe I start. Yeah, I was thinking about this work just before you presented the conclusion slides. That it seems to generalize this notion of weak revealing MDPs. When you're replacing the revealing action sequence business with revealing segmented policy kind of thing, right? So what do you say about that? Like, is that true, or is there some nuances there that I'm missing? So yeah.
Could you?
Yeah, I'm just thinking that, okay, so the main tool ends at the end. The main tool happens to be optimistic MLE, just like in previous work, and the whole business becomes like this incremental design of experiments to push the identification of the underlying system, including whatever observation distributions, or in this case, distribution over the latent state you have. And so there is a lot of commonality to the previous work. It seems that the main difference is that in this work, you have to use this segmented policy class to deal with the fact that you have this latent state. And so that's like creates a common ground. So you could try to propose a criterion like, okay, let's assume that somehow states are revealed. And in your case, the state, of course, would be basically the latent state plus the current state.
Exactly. Yeah.
Right?
Yeah.
So the state is revealed after I execute such a segmented policy. And I need to search in the space of that policies to find out what is the revealing segmented policy, and then optimistic MLE on the top of this basically solves the problem. So it's like a common generalization of the two things, because if I understand it correctly, at the moment, your results do not apply to the weak revealing case. So it's like, is there something that, generalizes these two statistically tractable cases of MDPs?
So one thing that I think could be interesting to unify those is, so first of all, I think OMLE it's a very general thing. It doesn't care about whether it's POMDP, MDP, or even functional approximation, as long as the model hypothesis is realizable. So it's a very nice distributional the confidence set construction tool to match the distributions that you have observed so far. So I would say the main difference that I think the key discovery here was this off-policy evaluation lemma, which was defined in terms of this correlation coverage coefficient. Because the thing is, I will never be, in the worst case, I'll never be able to observe which latent state has been visited, which context has been visited. This is all implicit here. So the nice thing about the coverage coefficient is it is defined as the ratio between two different policies, but it is defined over the true environment. So just one ground truth environment. So this correlation coverage is there is no ambiguity in this coverage coefficient concept.
I see. So it's localized to the actual environment.
Yes.
So that's an important point.
Yes.
Sure.
So if we can find some like off-policy evaluation lemma for weakly revealing POMDPs, which I think the Nanjiang's group has been studying these days, and if we can come up with a nice notion of coverage there, I think the recipe here. So the after we got the off-policy evaluation lemma, I think the recipe here might be applied the same to any kind of problems where you got the off-policy evaluation lemma in terms of that coverage. So yeah, I think, and I was also thinking that weakly revealing POMDP could also be interpreted in this way.
Yeah. Right. Okay, makes sense. Very nice. Very nice.
Great. Maybe we stop the recording in case there are some people that don't want to the question live.